over to me. Yeah, wherever you want to sit. Okay, come on. All right. You can sit. Somebody can sit at my desk. I don't care. Come on. Come on. Come on down. You're the next contestant. Okay. So here's the thing. I don't know how long this is going to take. I don't really know how it's going to go. But I know how to explain it, and I have it figured out, and it'll be okay. This is the worst day. This is way worse than Friday. I figured that out. It's just the worst. So if we can do this, we're fine. Okay? So anyway, common ion effect. And I think on these slides like this, I think this stuff just goes down better if I just write it out, and I don't know why. But basically what they're saying is if I throw some potassium fluoride in there, what's going to happen? So let me I'm just going to write it, and if you don't like that, I'm sorry. So if I have some hydrofluoric acid, and when y'all did your homework last night, you probably saw that that's a weak acid, and that's going to trip you up because the other group 17 with hydrogen are strong. So don't let that one mess you up. Okay, anyway, so I'm going to add it to some water, and this is a liquid, and this is a Q, and all that, okay? And I'm going to do reversible arrow because it's going to go both ways. But this is going to break into H3O plus and some fluorine. And this is a conjugate base, and it's a fairly strong conjugate base because it's a fairly weak acid. Okay, so whatever. Now that part you should be okay with after doing homework last time. Now what this little slide is saying, hey, what if I throw some KF in there? It's not an acid, this is a salt. Is this soluble? Yeah, group 1 stuff soluble, group 17 stuff soluble all day long because they have that small charge and a very weak Coulombic attraction. Okay. So anyway, what happens then if I throw this in the beaker, you got to think about it like being over here. It's going to shift the equilibrium that way. So the HF, the hydrofluoric acid, is going to break apart even less. It's going to have a lower percent dissociation. How does that make you feel?
So it'll make the solution more acidic?
No. Let me show you. Let me. No. I got it. Hang on. So look, if it shifts the equilibrium this way, when that happens, it goes more back into making these HF molecules. And the HF molecules, an HF floating around in water will not affect the pH. It's only the hydrogen. When the hydrogen does this, then we're going to have a lower pH. So it's actually, and this is exactly like that's on one of the release exam questions you just picked up. If you add a common ion, it shifts the equilibrium this way. So that pulls these out of solution. Go back this way. So this is going to make the pH actually go back up. It's going to be less acidic because you're going to have less hydrogens break off of this.
So like the actual acid itself is not what makes it acidic.
So these all day long, just chilling out. Nothing to do with the pH. It's where the water comes along and takes that guy and makes this. And that's what we do when we calculate pH. pH is equal to the negative log of the hydrogen ion concentration of this. Not that. So, does that answer your question? It's a good question. You okay? I feel like I'm going to have to come back to this spot screen a lot today. And I'm alright with that. So anyway, so since KF is soluble, this experience 100% dissociation. This F is a common ion, drives the equilibrium back to the left. And so your pH is actually going to rise. Man, this is just a throwback to Le Chatelier. You okay? All right. Let's look at another one of those. So here I have ammonia. Ammonia is a weak base in water, and it's going to make hydroxide and ammonium. So what if I have some NH4Cl? So back to my other screen. You see, everything's fine over here in this little white place. It's totally fine. So then I'm going to give it some water. I'm so used to having to do these little states. Anyway, so here's my conjugate acid, and then I got some hydroxide. Good times. Now, if I add ammonium chloride, first of all, this is the chlorine is the conjugate base of a strong acid. Is this going to affect pH at all?
No.
No. So this is though, right? So I basically, from last unit, I have added ammonium. So when I add a reactant or product, it's going to shift to the other side. So I'm going to go back this way, and that means I'm going. That means that both of these, not just this, but both of these are going to go down. So now I'm going to remove hydroxide from the solution. So my pH is going to be less basic. My pH is going to come down closer to neutral. Okay? Alright, so anyway, the NH4 is a common ion. It's going to shift the equilibrium back to the left. pH is going to drop. So, the thing about buffers, is you want to have a weak acid or a weak base, and what they're going to do is they're going to actually react with any strong acid or strong base, and they're going to be able to help neutralize them. Before we go on to this, why don't you guys practice just one little question. If you flip to the back of this PowerPoint, I think number 1 was very appropriate. So give number 1 a little try, because this part right here. So anyway, if I have a buffer, what it can do is, I'll just kind of, a really, really super common one is that acetic acid and acetate. So I'm just going to be like that lady on that movie, and I'm just going to draw this in here. Whee! So a buffer would be having something like the CH3, COOH. So like my acetic acid, okay, and then like some acetate, and then some acetic acid, and then some acetate. And so here's the thing. This acid, if it is exposed to a base added to the system, then it's going to react with that, and it's actually going to make water, and it's going to make this. And if I add acid to the system, the acid is going to react with that. It's going to make water, and it's going to make this. And so what you have with buffers is you have a weak acid, and you have its conjugate base, and they're floating around. And if you happen to add a little acid to the system, then the base is going to pick it up and react with it and neutralize it, right? Acid-base neutralization. And then this acid floating around here, this guy, if I add a base to this, then it's going to make water and help neutralize it that way. And so they can both sort of do that. So just thinking out loud, if I were to take a little drop, and I was adding maybe an NaOH to this, well, which one of these two would it react with? The acetic acid, right? And let me show you what that looks like, okay? Yes, sir?
Are you adding a strong acid or a strong base, or can it be like a weak acid?
It's going to be a weak acid or a weak base. But the thing about it, you don't ever have to deal with math with weak and weak. You don't ever have to do that. So this is always
It's always going to be, a strong acid and a strong base.
And the thing is, these buffers are always going to be weak acids and bases. And the reason they need to be weak is because if I had a strong acid in here, like hydrochloric acid, the chlorine is not going to be able to do anything, right? This doesn't do anything to pH. It's not going to be able to neutralize anything. It's just always a spectator. So you need a weak acid and a weak base, because they got a little acid going on, a little base going on, then they can both kind of help you out. So let me just, before I go into math and things, if I take and add some sodium hydroxide, is the sodium going to do anything?
No.
No, so I'm not going to write that. But if I add, you guys told me that the acid is what's going to do this. And so if I add some, hydroxide there, then I'm just going to make water. And I'm going to make my friend that's already in the beaker the acetate. Now look at that for a minute. Make sure you're okay with that. You okay with that? Alright. Well, okay, cool. Well, let's just say like I add a little acid up here. I add some HCl. Which one of these, the acetic acid or the acetate, is going to neutralize that? Oh, okay, well, let's just look at what that looks like. That ain't going to do anything. So, I got H plus, or you could go H3O, whatever you like. And then, so I'm going to take that and throw in my acetate. Did I miss a C? I did. There. That looks fun. Anyway, and so look what I'm about to make. And do you mind if I just make this a hydronium? Is that okay? I'm going to make water. And I'm going to make my acid friend. There. So do you see when I add a little acid, I'm going to just make the conjugate base. If I add a little base, I'm going to make the conjugate acid. And they're going to float around in here, and they're going to be able to soak up quite a bit because they're just going to go back and forth. And we're going to do some math that shows that the pH really isn't going to change that much as long as you have some of the conjugate base and acid in there about the same concentrations. How y'all doing? Okay. It's great. It's good to know. I feel like I'm going to have to come back to that screen. Alright, so here's the definition of a buffer. A good buffer has to be a weak acid and its conjugate base. And so what you're typically going to do is to add that conjugate base, you have to add extra, right? The reason you have to add extra is because the acid is weak. It's not going to break apart. If you just add the acid, if you just add acetic acid to water, it's going to stay as acetic acid. And then you're going to have 0.0004 pieces come off. Do you see what I mean? So you're going to have to take something like sodium acetate and throw it in the beaker, and then you'll have your conjugate base in there. Or, so it can also be a weak base and it's salt. So it's a weak acid or a weak base. And that's good. And then, like I said, you can add small quantities of strong acids or bases, and the changes in pH won't be that big. That's the definition of a buffer. Okay. Alright, so, like I said, and I kind of already mentioned this, when I have a weak acid, equilibrium is going to lie far to the left. The Ka of acetic acid, you just did it, was something times 10 to the negative fifth, right? So that means when the equilibrium constant, the Ka for this acid, when it's little, the equilibrium lies over here. So in the water, I'm going to have a bajillion acids and like 2 of these guys, right? And so I don't have much conjugate base to be able to buffer any added acid. So what you're going to have to do, like I said, you're going to have to come over here and you're going to have to purposely add a salt that contains its conjugate base. So you're going to add something like sodium acetate, and then now I'm going to have lots of conjugate base. So I have lots of acid, I have lots of conjugate base, but you have to make the buffer by putting in that salt, that conjugate base with the salt in it. So the system has lots of acid to react with strong bases and lots of conjugate bases to react with strong acids. And so when you look at a good buffer, you need a high concentration of not just the acid, not just the base, you need a high concentration of both. And then you'll be able to neutralize quite a bit of added stress. So ideally, you want a weak acid and weak base, and then you want to have high concentrations of both. And then ideally, you want to have equal and high concentrations of both. Right? So they'll be able to withstand pressure either direction. Still okay with me? Okay. So, like I said, the ability of a buffered solution to accept protons, which that's, neutralizing an acid, that's a hydrogen off an acid, or hydroxide, that's the definition. And like I already said this, but you want a high concentration, HA, this is about to be real important, HA is the acid, and A minus is the conjugate base. Are y'all okay with this? Means acid, if I lose the hydrogen, it becomes this. This is about to be in a formula that's going to make you cry. So, acid, conjugate base. So, you want to have high concentrations of both. And the higher concentration, the more you can buffer. And that means you can neutralize hydrogens or hydroxides, and the best buffers will have equal. You know, when we did that lab the other day, and we said that pH was equal to pKa, and it was in the middle of that little curve. That's about to make sense to you. Isn't that going to be fun? Y'all look super excited. So not yesterday, last week when we did the lab, and then we had the pH was equal to the pKa of the acid. I'm about to explain to you why that worked. It's all going to make sense. Maybe. All right, so this is the Henderson-Hasselbalch equation. This is on the yellow formula sheet. This is the one. It's okay. This is the only one that you don't have yet. Okay, so we looked at acid-base equilibrium, that big chunk in the chart, and this was the one that we skipped that we were coming back to. So this is given to you, okay? Now, look, I'm going to go back and I'm going to draw a titration curve for you, because I don't want to just, they've changed the test, right? You can't just memorize that formula and everything's okay. That doesn't work. So anyway, we're adding. So if I add base right here, add base, and then we have some milliliters, blah, 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 and then we have pH, 1, 2, 3, 4, 5, 6, 7, doesn't really matter, whatever. Okay. Anyway, so we have this curve, and then it goes like this. And here's our equivalence point. Don't really want to cooperate with me. So if this was 20 milliliters, then right here at 10 milliliters, do you remember I told you like at half the equivalence point, pH equal pKa? You did all this already, and you were okay with it. So right here, pH equals pKa. Well, let me just tell you a secret. As I'm adding that base to this acid, every little drop, what I'm doing is I'm taking that acid and I'm making a conjugate base from my acid. So I'm taking my acid and I'm turning it into conjugate base. The middle of this line, don't just stop looking at your papers. The middle of this line, they're equal. In between this point, where it's neutral, you have equal acid. This one, you started out titrating acid. You have equal acid and equal conjugate base. Every acid particle makes a conjugate base particle. Halfway between, you have them equal. What's one divided by one? Or one? What's something divided by itself?
1.
So if these are equal, it's going to equal 1, right? Are you okay that this midway equivalence point, this midpoint is what it's called, the midpoint, these are equal, and this is equal. Conjugate base. Are you okay with that? Okay. So logs, right? Like a log of like the log of 10 to the 8th. That's 8, right? Okay. Well, like, basically when you take a log of something, you're able to bring like the exponent of the 10 down, and then it's like a real number, and that's how that works. So if I did that, if I took the log and this was 1 here, do you know what the log of 1 is? So at the midway equivalence point, pH equals pKa, because the log of 1, where these are equal, is 0. So this is not a thing right now. Oh, okay. How you doing? Remember, log just takes the number down, and so 10 to the 0 power is 1, right? So, right. So that's how that's working for us. Anyway, this is so much fun. I'm having the best time. So, what's going to happen? This formula is only for that flat part of the titration curve, and that's the buffering part of the titration curve, and it deals with buffers. Anytime you have a problem with buffers, it's going to look awful, and you're like, I have no, and like your normal like stoichiometry tricks will kind of work. I've actually solved buffering problems without using this, like on accident, without realizing that this was way easier. You can do it, but it's like really it's convoluted. So if you have a buffering kind of question, this is your go-to guide. And it's not that bad yet. So if you have a buffering problem, this is your thing. Notice that this is for weak acids and bases. This is when we're talking about a buffer. Okay, so let's just talk about logs for a second. We need to do that. I know you don't like me. I don't care. This is what's gonna give you trouble. Okay, watch. What is this answer? Good. Right. Good for you. What is this number, though, actually? 0.001. Okay. And so if I took the log of 0.1, is this going to be, or 0.01, or 0.1, is this going to be a positive or a negative number? It's a negative number. Negative. I didn't do this. This is the same thing. Okay, sorry about that. So, okay. We just did this, right? That happened. Okay. Here's the thing. This looks real. This is like Google G, you know? Man, I couldn't actually draw that if I meant to. Now, that's fine. You're good with that, right?
Yeah.
So the logs of numbers less than 1 are going to be negative numbers. Because scientific notation, you're going to have a negative exponent. The numbers bigger than 1, you're going to have positive answers. So here's the thing. Okay, watch. We're not taking logs of just numbers. We're taking logs of a ratio. Isn't that fun? Super fun. Let's think about this. Think about the numbers, okay? This is just the second part of this formula. This is just like that last part, plus this. So if I'm taking this and, I needed to add something to it, like I needed this to be a positive number, right? I need this to be a positive number. So this has to be a number bigger than 1. Now don't say anything out loud. Talk to your neighbor. Which one has to be bigger if I want this to be a positive number? A minus or HA? Talk to a neighbor. Which one has to be bigger if I want to get a positive answer? Find a friend. I'm not listening to you. See? I've turned off my superpowers.
I just thought I tried to go along. Alright, so water out of ions, is that like process reversible or is it?
Yeah, it always happens.
Why does acids and bases automatically neutralize the cell? Because if it's in water, shouldn't it just...
You're asking me why we can't pay off the national debt with a couple pennies. Right, it ain't enough. It's drops in the ocean. It's a tiny number.
Like why?
See what I mean? There ain't enough of them.
Oh yeah, because that's the
Right.
guys.
Super tiny numbers. Okay. Sorry, whoever's making my draw. Catherine, what number has to be bigger if I want to get a positive answer off of this? The conjugate base. And that's cool. Like if I want this to be a positive number, like if this was 8 and that was 2, then I'd have like 4 and, then I'd have a positive log. It wouldn't be super big, but it'd be positive. And so if I wanted this to be a negative number, then I'd want this answer has to be less than 1. So this bottom number has to be bigger. So that's like the math of it. You just have to think about it a little bit. Okay? Sure. It's totally fine. I just wanted to take a little pit stop into math world. All right, anyway, so there's that. You have a question? Oh, I saw movement. All right, So when we choose a conjugate acid-base pair, what's going to end up happening is they're gonna tell you, I need a buffer with a pH of 4.3. So you need to choose an acid with a pKa close to 4.3. And then you're going to have to play around with these concentrations to make this pH be bigger or smaller. Let me show you what I mean. Like if they wanted a pH of 4.3, and let's just say the pKa was 4.2, well, all of this crap right here has an equal 0.1. It's a positive number, right? So I'm probably going to have a little bit more of this. And that's kind of where we're going with this. I mean, you'll be able to fill these numbers in and do math, and it'll be fun. But I didn't want to just go to there. Anyway, if these are equal, then pH equals pKa, and that's the titration curve midpoint. That's nice. Good times. It's helpful when choosing a conjugate acid-base pair. If the buffer needs to have a certain pH, like I said, you're going to want to choose the pKa that's close. We have some practice for that, and that's where we're starting with this. That's the beginning. And I have a POGO for this. The POGO at the beginning of the class, that didn't really help us a lot. I'm just going to keep drawing pictures. Okay, is that all right? Let's just keep doing that. All right, so pH equals pKa. Like I said, pH equals pKa when these are equal, because the log of 1 is 0. I've already explained that 3 times. There's 4. Okay. Buffers made from very weak acids and very weak bases are going to have high pH values. So let's use our mental math powers. This is where you're going to have to go when taking the AP exam. If the pKa of an acid is 1 times 10 to the negative 10. So if I want to look at pH, pH is the negative log of that. So my buffer pH is going to be around 10. And y'all saw this because acetic acid was a weak acid and our equivalence point was like 8.6. So if you have a very weak acid and its Ka value is 1 times 10 to the negative 12, then your your pKa, when we look at them and make them even and everything, we're going to see that the buffer is going to have a very high pH. So, but you really see a whole lot of reactions. They want to keep it 12, but it's pretty common to see something around 7, 8, 9. Buffers made from stronger weak acids and their bases are going to have lower pHs, and that's just because if the pKa is like, see how this is stronger than that, 10 to the negative 4, your pKa and pH is going to be around 4, and that's good. Do you remember we talked about pKa? The higher the pKa, the weaker the acid. And that happened. Remember? Yeah. Okay. So anyway, the stronger, lower number. All right. So here's the thing. When you have a buffer, even if, let's say that I create in my solution by buffering, 100 particles in relative terms. I make 100 particles of the conjugate base because I've neutralized added acid. When I neutralize added acid, I'm going to make a conjugate base, right? And then I have only like 1 particle of the acid left. Well, what's that going to change the pH? Well, let's see. The log of 100, that's 10 to the second power, the pH is only going to go up by 2. So that's not a big pH rise, right? And so if it doesn't go up, except maybe the ratio goes 10, right? The pH is only going to go up by 1. This number gets added. So that's the cool thing about buffers. Even if you change the concentration of the conjugate acid or base by a power of 10, your only pH is going to go up by 1. That's nice. Okay? And so if this ratio is 0.1, there's your negative number. See? So, and that's less than 1. We had this conversation. So adding small amounts of acid or base to a buffer solution causes very small changes in pH. All right, so let's look a little bit at picking the right acid for our pKa values. Here we go. We're just going to do the A part first. Suppose you're required, this is where we're going. Suppose you're required to create a 0.5 liter buffered solution where the HA and the H minus have similar concentrations. So if I have, and I'll go to the next screen because this is a typo right here. But using the information, select the weak acid and conjugate base pair that you would use to create a buffered solution with a pH of 4.8. And so if you go to the next page, don't do the rest. We're coming into this. Don't look. Use your calculator, use your friend, and pick, you can see. But pick the one that would give you the pH closest to 4.8. Don't look at the, hang on, I have the power. I know you already looked. There. A lot of times you can kind of eyeball these, but I mean, this is going to be around 4-ish or above 4 though, and this is going to be around 5, so you can't really tell which one's going to be closer to 4.8. You do kind of need to use your calculator. Y'all do y'all have a calculator? Are you calculating the pK? Go get a calculator. Go team, go. What? Yeah, use mine. It's fine. So when you did the calculations, did you get that the pKa's were 3.18 and 4.74?
Mm-hmm.
And so which one would we want to choose to make the buffer? Acetic acid, right? Because we want the buffer pH is going to have to be 4.8, so we're going to have to do some stuff with that ratio to make it be 4.8. So what I want you to do, let's practice this one little skill before we move on to the other part. When we change that ratio. So how was 5A and 6A? Great, good. So that was just the first part, right? The whole question was that we needed to make this buffer. It needs to have a pH of 4.8. And then it needs to be able to prevent a significant pH change if I'm adding 0.125 moles of sodium hydroxide. So these are scary. The best thing to do as far as starting is like get your, I'm going to the white screen. I'm going back to the place. So write down your Henderson-Hasselbalch, okay? This is on your formula sheet. Why don't you go ahead and find it on your formula sheet, and then you won't. Here, I got it. There you go. There you go. I got copies over here. So find it so you know where it is, right?
Oh my lord.
What's the matter? Oh, you'd be alright.
Yeah.
So pH is equal to pKa
That'll be alright.
plus the log of, and I just remember the A goes on top, just alphabetical order, good times.
Way to remember it.
Is everything okay?
No.
When you're
Are you afraid?
Very confident
You're
good
allergic
at math.
to
Yeah. It was coming, she tried to hit it.
Alright, just turn the light off and it'll fly out. It'll
Or
go.
towards this
Boy.
It'll go.
Alright.
Stop breathing. No, I'm just kidding. Anyway, so the pH, I don't have my paper somewhere. Okay, so the pH they wanted was 4.80, and then we found the pKa is 4.74. Have I blown your mind yet? You okay? All right, cool. So now we're just gonna do some math. We're gonna solve the math. It'll be fun. All right, now what's my unknown here? That big chunky thing in the brackets. I don't know what that is, do I? Don't know the things. I don't know. So I can start to isolate that. The way I'm going to isolate it is I'm good old algebra. I'm going to subtract. This is hard. I'm going to subtract. This ain't the bad part. I'm going to subtract 4.74 from both sides. And so I'm going to get 0.06 is equal to the log of my conjugate base. And I guess I could fill these in. I'll do it on the next step, I promise. Honestly, don't remember what the acid base was. I have. Oh, yeah, okay, I know that. Alright, fine. So anyway, I have to isolate this still some more. So what do I have to do with this log? Yeah, so I'm gonna be like, whee! That's how to do, right? So I make logs go away, raise stuff to the power 10. So I have 10 to the 0.06 is equal to, and I'm gonna go ahead and fill in my stuff here. So it's just acid. Alright, cool. So punch buttons in your calculator. 10 to the 0.06. That's about 1.15. Yeah. So 1.15 is equal to this ratio. Do I know how much of this is in the beaker, like at all? I don't know anything about this. I don't know anything about this acid and conjugate base, except that I know the pKa, and I know that I'm going to need to neutralize some amount of sodium hydroxide. Oh, it said 0.125 moles. Do you see these are brackets? Isn't that? Yeah. So that's molarity, right? So what I'm going to do is we need to, so you should be on like that next little box there. We got 1.15. So on the top of page 3, like this is that first box. You good? Okay, so in the next part, go back to the page. Make sure y'all with me. When we did all this, and I think they might have been happy with that, and I have 1.15, and so that's fine. But the next thing we have to do is we're going to have to, since we're dealing with molarity and concentrations for this thing, we need to figure out the molarity of the sodium hydroxide. So they did that up here. Take the moles and divide it by the liters. I can go back to the other screen and do this if you want me to. You okay with this part? Because we have no idea, they have given no information on the molarity or concentrations of the acid or base in our buffer. We have no idea what we're going to throw in there. But we know the purpose of the buffer is to be a pH of 4.8, and we know that we need to be able to accept this molarity of sodium hydroxide, and so this whole formula is based off of brackets, off of concentration, and so I need to know the concentration of sodium hydroxide. And so now I can take this information and go back to those brackets. So anyway, what's going to end up happening, I'm going to go back, make sure you got me on this one. This isn't making anything better. Makes 0 things better. I'm going to go back to my little beaker. My invisible beaker. Going back to my invisible beaker. And I have this guy. If I'm making any board right now, you got the rest of the problems. Peace out. Seriously. So that's what I have in my beaker, a bunch of those. Don't know how many I'm going to have to put in there. And I'm going to be adding sodium hydroxide. Doesn't matter. I'm adding this. Which one of these two is it going to react with? The acetic acid. By what concentration of acetic? This is 0.25 molar for my concentration of hydroxide. So what concentration of acetic acid is going to be needed to neutralize that? 0.25 of these guys. Now watch what happens. CH3 COOH plus hydroxide is going to give me acetate, water. Look. 0.25, 0.25. These go down by 0.25. Yes? This goes up by 0.25. Do you see why? Let's soak in. Okay. So, when we neutralized when we neutralize this hydroxide, it's not like it just makes water. Because it's a weak acid, it's going to make water in its conjugate base. And so not just the acetic acid is going to go down, but the conjugate base, the acetate is going to go up. Because I made it when I neutralize this. You okay? All right. So this is going to increase by 0.25 molar. I just showed you that. This is going to decrease by 0.25 molar. Can I have the denominator of a fraction, can I have it be 0? No. So what I need here, I need this bottom to be at least 0.26. Then I'll have 0.01 left over. So you just add a little bit extra, one more, above what you need. Okay? That's not it yet. But, so, this has to be at least 0.26. At least. The bottom does. And the top, we'll get to the top in a second. The ratio. Do you remember the ratio? Do you remember? It was 1.15. Do you remember that happened?
Yeah.
Okay. So completely unrelated numbers. I want you to do this in your calculator.
Erase her again.
I know. I want you to do this in your calculator again. These are unrelated numbers. I'm going to use 1.15. 5 times 1.15 divided by 5. Yes, I already know that you know that, but you don't know that you know that, and you'll screw it up. So, if this ratio has to be 1.15 when I divide, doesn't it? What was my molarity of that bottom one? What's the top of this going to be?
0.26.
You see it? Do you see it?
Yeah. Then you just can't
And
drop.
And that's how to do.
And that would go.
Did you get it?
And then you just can't
Yeah,
drop.
it's 0.29.
Yeah. Well, no. I don't know. No, you don't cancel anything. We gotta make this. We gotta make this in a beaker. We're not canceling things. The question asks, what is my concentration of my conjugate base? What's my concentration of that? And what's my concentration of this? I already know the bottom. The bottom is 0.26 molar. So you're not canceling anything. If you cancel it, you'll get 1.15. Yes, we already know that. It's not helping us. But the top though, what's this? What is this when I multiply?
0.29.
30.
0.29. Not yet. Make sure I send that right.
So those are so I need to put in my beaker these things.
Oh. But could it be like 0.29 or 1?
Sig figs.
3
Because they gave you 0.2.
Yeah, it's 0.29.
Yeah, and so but in their answer they get 0.29, and the reason they get 0.29 is because they have 1.1 in there. We want 1.15. Okay. Alright, so let's look at their little math. There's their math. They got 1.1 instead of 1.29. So the end of the answer, the end of it, you need 0.26 and 0.29. We found the ratio. We know the pH. That's it. That's all. That's all. That's all of it.
Oh.
That's it. That's the worst thing ever.
That's still pretty.
That's not.
It is like really.
I don't get it.
So.